All right, why don't we start? I'm Dean Wampler. This is the London Eye. I like to inflict my photography on my audience, so if you're bored with the content, you got something to look at. I've been trolling the Hadoop community since 2012. This is my LinkedIn profile. I started doing Hadoop consulting in 2011 and was immediately unimpressed by the quality of the tools that we had to work with. And felt that there was a much better way. We should be using functional programming. We should be using languages like Scala. I struggled in the darkness for a while, and then we've actually gotten to a much better place. So this is kind of a story of that transformation. If you can't see the slides from the back, you can get them right now at polyglotprogramming.com/talks. That's my vanity website. You can spam me on Twitter and so forth if you like. And so why Spark? Why type safe? Well, obviously, as you probably already know, Spark is written in Scala, and it's sort of the big hotness right now in the big data space. And TypeSafe is rolling out commercial support for Spark, running on top of Mesos as a clustering system or standalone mode, which I'll briefly get into. So if you're not using Hadoop, don't need Hadoop, then you know who to talk to, I guess. But you can find out more about what we're doing with Spark and big data in general at this website page, Reactive Big Data at the TypeSafe site. Okay, enough advertising. So let's talk about where Hadoop was in around 2013, which is when Spark began to take off, but just kind of set the stage a little bit with a little history and why I was trolling the interwebs at the time. So, roughly speaking, a Hadoop cluster looks something like this, and it's sort of typical of any sort of distributed cluster. There's some masters involved. Hopefully there's some resiliency through failover and all that, and some worker nodes. In this particular case with Hadoop, when you submit a job, you're actually submitting it to a resource manager called Yarn, yet another resource negotiator, that decides how to break your job down into tasks, and those are separate JVM processes, and how to schedule them around the cluster given the resources available, especially when you're in a busy cluster with multi-users and multiple jobs of various kinds. And usually the data is stored in the Hadoop distributed file system. Its master processes are called name nodes, and it has data nodes that know where all the blocks are for your files, sharded across the cluster and so forth. So that's as far as I want to go into explaining Hadoop, except to talk about the compute model. So the storage was HDFS, the sort of minimal configuration. But you needed some way to process this data. So MapReduce was this compute model that was invented at Google, probably late 90s, but written up in a very well-known paper around 2003. And it was cloned into Hadoop as a sort of a clean room implementation. And it served us pretty well for a long time. Hadoop kind of went mainstream around 2008 after incubating inside Yahoo for several years to sort of reach production quality for some definition of quality. But it's kind of hit the end of its life, and that's kind of what this story is about. Basically, with MapReduce, you get one map step and one reduce step, and you can glue as many of those together as you need to implement your job. Wash, rinse, repeat. In case you don't recognize that, that's a common algorithm printed on shampoo bottles in America. I'll let you decide if it's a good algorithm. There's some flaws in it, perhaps. But nevertheless, that's sort of the idea. You just basically have these two big hammers that you can smack your data with, and that's the best you can do. So just to make this a little more concrete, let's talk about an algorithm that's slightly not trivial. The most trivial algorithm is something called word count, where you just count words, as the name implies. But a slightly more interesting case is the basis of search engines, which is the so-called inverted index, where, say I'm reading in all of the interwebs, all the web pages on the internet, and I want to find, for a given word, which pages reference that word. So, and that's the sense that it's inverted. I start off with like document IDs or URLs, whatever, contents of the documents, and then I'm going to invert that into words and then a list of documents. So if you've ever looked at a web log, you've probably seen a lot of entries about web crawlers that are constantly walking the internet, finding all the web pages, and basically recording a simple data structure or table, whatever term you want to use, that has some identifier for that place on the internet and then the contents of what was found there. And this is, running typically nonstop at places like Google and Yahoo and so forth. And then what was done, say 10 years ago, especially at Google initially, was, periodically, maybe every hour, every day, something, you would kick off these MapReduce jobs that would process that data and turn it into the inverted index. And the gist of it is that, you're writing these big contiguous blocks on hard drives because you want to minimize the time it takes to seek across the hard drive. So you just want to, park the heads and then start reading. And each of those big blocks, which are typically megabytes in size, is going to get a dedicated JVM task, in this case called a map task. And it will, read in that data and do some processing. And in this case, it has a very simple task. All it has to do, and I know this is maybe a little hard to read, but it's going to spit out key value pairs where the keys will be the words that it found, on each line in that data set. And then the values will be maybe a nested tuple of some identifier of the location. In this case, I'm just going to pretend that it's Wikipedia data, and I'm just going to use the URL. And then a count the number of times that word appeared on that page. And that data then goes into, so you write that code. The map task is code you write. Now, if you're paying attention, you should be saying to yourself, wait, that's not map, that's flat map, and exactly you're right. So this is really ought to be flat MapReduce, but let's not be too pedantic. Anyway, so there's a sort shuffle process that Hadoop gives you where it sorts the keys locally, and then it shuffles these key value pairs, and that's actually a technical term you'll see used a lot, shuffle, where I'm going to move those key value pairs over the cluster network to the reducer tasks. And the idea is that I want to get all the same keys showing up at the same reducer and then build up the final record as I'm showing in the next slide, where let's say the first reducer task gets all the keys that start with H. And it turns out in my little made-up data set, if the word was HDFS, it showed up in 3 documents. And so the final output from the reducer that it gets from all these mappers will be, one record for HDFS and then a list of 3, document IDs and counts. And unfortunately, I only used all the words once, so none of the counts are that interesting. But that's pretty important, obviously. When you do a search, you don't want to find the pages that just happen to mention something in passing. You want to find the pages that are really all about this topic, right? So the count is pretty important. And I'd really like to sort it descending by count so that the most frequent counts show up first in my list. So that's the gist of it. It's a pretty simple algorithm. It's easy to implement in this very constrained model. But, so maybe it's not illustrating the problem, but there are actually a bunch of problems here. It seems okay, but actually we've got issues. One is that for most algorithms, it's actually non-trivial to translate conceptually what the algorithm's doing and this very limited 2-hammer kind of approach of mapping and reducing. And in fact, it became kind of a specialized skill that MapReduce programmers would learn all the little tricks of the trade to implement things. My favorite example of this is secondary sort. So if you write a SQL query that says like sort by count descending, name ascending or something, that's so trivial to write in SQL, it's actually incredibly hard to implement that in MapReduce in an elegant way. Well, actually, you can't do it in an elegant way, you just have to do it in a very tricky way. Another problem was that when you're coding at a low level and you're just kind of tearing tuples apart and you're manipulating stuff and you've only got these 2 big hammers, there's really very little room for the system to do any optimizations for you. So if you want to improve performance, you end up having to do that yourself. Rather than what we would really like, which is like SQL, a high-level language where I express what I want to happen, and then under the hood, some magic happens that makes it as fast as possible. And I don't really have to know a whole lot about what's going on. At least in principle, that's what we would like. But one of the serious problems that led to the downfall of MapReduce was that I mentioned that you may have to sequence several MapReduce jobs to actually do the full algorithm. But the runtime has no idea you're doing this. All it can do is simply dump all the intermediate data to disk, and this could be terabytes of data in some cases, and then read it all back into memory as the next job kicks off. It has no sense of this data flow that you're building up, the graph of processing nodes that it could then manipulate in some way, or maybe cache data in intermediate steps and so forth. It just can't do that. So you get terrible performance, and just fixing this problem alone, which tools like Spark do, can give you sometimes like 2 orders of magnitude improvement in performance just by eliminating this overhead. And the last point that we'll get to a little bit later, but it's relevant now, is that the nature of the kind of problems we're solving has changed too. And my favorite example actually is search engines like inverted index. You know, 10 years ago or late 90s, whatever, it was okay maybe if I made edits to my pages on the internet and I didn't see the results for hours in the search engines. But that's not okay long term. That's a competitive disadvantage. I would really like to see those edits show up immediately. And, you know, if I'm like editing a news site and then some, you know, one of my readers goes searching for, you know, updates on some breaking news story, I'd like them to actually find my information as quickly as possible. So even though some things can be done in this sort of batch mode, they're actually better if they can be done more quickly. The way I like to put it is I have data arriving and I want to minimize the time between that arrival of data and extraction of information from it. So we want to be able to basically process streams of data. Well, Spark was embraced by the biggest Hadoop vendor, Cloudera, in late 2013, which is why I picked 2013 as the sort of backdrop. And it was at that time that, you know, we sort of reached this critical mass of awareness that we had to do something new. Spark started in around 2008, 2009 as a research project at Berkeley University in California. And interestingly enough, it was actually started as a demonstration project for the Mesos clustering system. And if you read the Mesos paper, it actually has this humorous paragraph where it says, to demonstrate, you know, how this works, we created this little example project called Spark. But then it took on a life of its own and gradually got more and more powerful, more capable, more scalable. And you know, sometime around 2013 or 14, it actually became a top-level Apache project, and it was embraced by the biggest Hadoop vendor, Cloudera, as the successor to MapReduce. And that put it on a rocket ship. It's now like certainly the most popular or most active Apache project, and it could even be the most active open-source project in the world, although it's certainly in the top 10, let's say. Well, even though it started as kind of a very integrated with Mesos, they actually abstracted over the notion of clustering, so we have a bunch of options, which is very powerful for being able to use it in ways that are most appropriate for your needs. So it does now run on top of Yarn, the Hadoop scheduler or resource manager. It runs on top of Mesos, and TypeSafe is actually working to improve the support for Mesos. You can run it in EC2 on Amazon. There's a standalone mode if you just need like a static cluster, relatively fixed for a specific purpose, you know, very lightweight, you know, and not a lot of change going on. It's a great mode to use. And it's now being bundled sort of in an integrated package with databases like Cassandra and React, actually. Basho just announced React support recently. And there's also a local mode that I didn't put here, so I can run it on a laptop. And boy, that is such a great thing. We get used to the fact that we can actually run software in debuggers. Well, you can't do that with MapReduce either. You had to set up this sort of mini one-node cluster on your laptop just to run MapReduce code, so it was incredible pain. But now I can just run this like a regular JVM process when I'm developing stuff, or I'm working with data sets that are small enough where that's good enough. So, some of the things it gives us, though, to address other problems with MapReduce is we don't just get these big hammers, map and reduce, or flat map and reduce, as it really is. We get lots of fine-grained operators, the sort of things we just use every day with SQL or Scala collections like map, flat map, filter, group by, you know, etc., fold. We just get those, and we can use them, compose them together to create the data flows we need. The core abstraction inside Spark is something called a resilient distributed data set. And it looks schematically like this. Your data is actually partitioned across the cluster. So this might be on 4 different nodes, or maybe, let's say, some of these partitions are on the same node and others are on other nodes. But I get the parallelism that all the operations I'm going to apply to the data can just run in parallel on these partitions. And it's resilient in the sense that because Spark has the graph of computation that is used to create any stage or any of these RDDs at any stage, if I happen to lose one of these nodes, it can go back and reconstruct that partition. Now that could be expensive, so there's also ways you can say, please cache the data at this point because I'm either going to keep using it over and over again, or I don't want you to have to go back to the files to reconstruct to this point. So there are ways you can get around the performance problems there. But nevertheless, it's really good about being resilient in this way. It's actually written in Scala, and there's a nice quote by Matej Zaharia, who was the grad student and now founder of Databricks, who created Spark, that he was looking for a language to use. He wanted to use the JVM because it's a great platform for this stuff, and he picked Scala. Again, this is like 2008, 2009, because it had the right abstractions that they needed, like closures and stuff like that. But there's nice APIs for Java, for Python, and R, which is the language statisticians and data scientists like to use if you haven't heard of it. And the nice thing, too, is that some recent additions to Spark have added like query optimizers internally, so that, in fact, today, you can write code in any of these languages and it will run just as fast. And that's like a first for the big data world. Again, back in like 2012, 2013, if you wanted the fastest performance and your data scientists were using Python, they literally had to take that model, hand it to some Java engineers, and hopefully they would actually port it successfully and accurately to Java. A terrible way to work. Now, there's still obviously production issues about just writing up a script and then throwing it into production, but nevertheless, your data scientists can take their Python code and deploy it to production, and it will run as fast as it can, which is a real benefit. So let's actually look at what the inverted index looks like. And just for comparison, we'll start with the Java MapReduce version and then talk about the Spark version. And it goes like this, so pay attention very carefully. So we're going to set some properties. Now I got to run things. Oops, now I'm going to map over stuff. I don't know what's going on here anymore. And now we're going to reduce it. So basically, I hope you got all that as it went by. Actually, I did not want to go through this in detail because it's a little early in the morning and I didn't want you to lose your breakfast. Also, I actually lied a little bit. This isn't really the full implementation. I'm not actually counting the occurrences, so I didn't actually keep track of which documents were most important. By the time I got here, I'd sort of lost the will to live and decided not to continue. So anyway, and I didn't actually show you all the, well, I guess maybe I did. I showed you most of the code. There's a few pieces missing. But, there's just a lot of low-level bit twiddling. I have to keep track of framework stuff, and it's actually just not fun to write this way. And it's easy to make mistakes, so I have to be very careful. It turns into several hours of programming, even if I know the API and testing, to make sure I didn't make any dumb mistakes. But it's just not a productive, fun way to work. And again, this is a simple algorithm, and it's still several hundred lines of code, or well, maybe 150. Hopefully you can read this. This is 6-point font, the whole listing. I wanted you to see it all together, right? So let's look at it in Spark, and this time we'll go a little bit more slowly, and we'll also put back in the counting that we want. So we do an import of a thing called a Spark context. That's our entree into Spark. That's how it knows to connect to whatever server we're using. So we start with imports, and typically you use like a Java object and just put this in a main routine. I'm just going to write what could also be written as a script in the Scala REPL, which is amazing that you can actually work with terabytes of data on a cluster just using the REPL when that's the right thing to do. So you create a Spark context. Actually, that first argument, local star, means I'm just going to run it on my local machine but use all the cores. So I can play with it locally, and normally that would be like a command line argument, so I can just take the code and run it on Mesos or run it on Yarn when I'm ready. I wouldn't hard code it normally. So this is where the data flow begins. And basically, I've got like 20 or 30 lines that's a single expression. I'm just going to sequence things together one after the other. So imagine I've got crawl data parked at this path on my file system, and I'm going to start loading it as text. So text file means I'm going to treat each line as a record. Starting with a Spark context. Then the first thing I'm going to do is map over each line and tokenize it into the path and the text, and I'll assume it's tab delimited data. I only want to split on the first tab because obviously there might be tabs in my text. I'll also assume there's no new lines in the text, that I got rid of those in my web crawlers. But, pretty basic stuff. So I'll return a tuple with the path and the text. And then I'm going to use flat map to tokenize that into words and then return the each word with the path, and I'm using a very stupid way of splitting it. I should use a real tokenizer, but nevertheless, I'm just splitting a white space. This is sort of an idiomatic way of counting in Spark. The first thing I'll do is I'll take those word path pairs, treat that as a key, and embed it in another tuple with a seed count of 1. And then I'm going to use basically what's equivalent to group by, and then counting the size of the group with an optimization called reduce by key, where it will bring together all those word path pairs of the same, and then apply this function to the thing that's left, which is the integers, and return a count. And so the output is shown in this box, where I'll get a unique word path pair, and then a count of 1 or more for the results. And one thing I want to mention at this point too, going back to this idea of runtime optimizations, everything up to the reduce by key could happen inside each partition separately. I did mapping, I did flat mapping, I could have thrown in some filtering, that kind of stuff. And there's no need to exchange data between each partition, whereas I have to do that when I get to reduction, right? So that means that Spark will actually take those steps that I wrote in what was the most conceptually easy way, a little piece of processing at a time, and it will actually combine those into one JVM process called a stage. So I don't have to do something like, oh gosh, I've got this mapping and flat mapping I want to do. I need to figure out some massive function that will just do it all at once so that I can run it in one process. Because I don't want this to run like 3 JVMs just to do each of these little steps. I don't have to do that. Spark is going to do this for me. To be clear, we're actually building up a data flow lazily, and it'll only be at the end when I actually tell it to run. But when I get to reduction, at that point, I am going to be doing that shuffle process of data. So at this point, it'll kick off a new stage, which will be ingesting the data coming out of the previous stage to do the reduction. All right, now we've got those word path pairs and counts. Now I want to get to the final result, which is I want to be the word to be the key, and then I want a collection of path and counts. This is my favorite line in this whole program. I want you to look at what's going on there. I'm just taking the 2 parentheses and just moving them. I'm doing this pattern match, and I'm just shifting parentheses. I don't know how you could make that any more concise. And if imagine doing this in Java, you'd need a tuple factory, abstract, meta factory, or something, right? But no, you just move parentheses and you're done. I just love this. It took me like 5 seconds to write this line of code. And then so this is you can obviously guess just looking at the code, what the schema is of the data that's coming out, right? Okay, group by key is another optimization. Basically, the key, by default, the key is always the first element of your tuple. So in this case, I want to group over all the words, just like you would in SQL. And what I'll end up with now are records. It'll be each unique word and then an iterator that'll have all of those path count pairs in it. And then the final step is to do the sorting that I mentioned I want to do. And once again, Scala collections save my bacon, as it were. So I'm just going to do sort by, and I'm going to take the input tuples. Again, this is inside that iterator. I'm not even in Spark at this point. I'm just doing Scala collections. But if I just return out of this function a negative of the count and then the path, it will do count descending and path ascending sorting for me. And the only reason I'm sorting by path here is because for unit tests, I don't want ambiguities where if the count's equal, I don't want the paths to randomly appear in different places. So that's the only reason I even care about the path sorting here. And I don't really need to do the make string either, but that just makes the final output a little bit prettier, but it's also not that important. But the main thing is I'm really just doing the final sort of those, that list of path and counts, and then just formatting it a little bit. And then finally, save as text file. We'll write out the results. And then when it's all finished, it will stop. And that's it. So hopefully you could follow that. Some of you can actually read this, I think. This is 14-point font. But the cool thing is that you've got these powerful operators or combinators if you're a functional programmer. A real person. But you get this sort of toolbox at your disposal, and you just start slamming out code really fast. You're not distracted by bit twiddling. You're not distracted by whatever crazy framework stuff that MapReduce imposes upon you, or J2EE as it reminds me of. You just do the data transformation you want to do step by step using these operators. passing the functions that obviously configure it. I don't know how you could write more concise code, unless maybe we could get rid of the case statements, but we have to have those for pattern matching, right? And it reminds me of another domain-specific language I fell in love with 30-some years ago when I was a physics student. Who knows what this is? Just shout it out. It's Maxwell's equations that describe electricity and magnetism. That your phones work because of this, microwave antennas, Wi-Fi, when it works because of this. I mean, what I love about this is it beautifully expresses the symmetry, but not quite symmetry, of electricity and magnetism. Electricity has charges, magnetism, as far as we know, doesn't. There's obviously details that are hidden behind the definitions of these capital letters, but I can take these equations and calculate anything about electricity and magnetism, at least in the classical realm, not quantum mechanically. But I used to have a T-shirt that had this on it that I would impress my friends with, but not girls, actually. That didn't work. But I just love this stuff, and it's the sort of thing where it shows me what I need to know, it hides what I don't need to know, and it lets me express what I want to say. And the Spark version took me about 30 minutes to write the first time I wrote it. It's gone through some evolution, but whereas that MapReduce program was not doing as much, but it took a lot more work. Well, when you have the right abstractions, the right core, which we've been looking at so far, you can layer on top of it other tools, and I'll focus on two of them and just briefly mention two more. And one of them that's extremely important in the data world has always been SQL or SQL. And sometimes what you really want to do is write a SQL query, especially if you don't know any other programming language. This has actually gone through a lot of evolution recently, and they now have this thing called a data frame API, and that name is inspired by similar APIs in Python and R. And it's actually the feature that gives you that optimization I mentioned a minute ago, that you can write in any of these four languages and you basically get the same performance. Because it actually, in fact, they're doing some heavy lifting under the hood. Even the Python code API is actually generating JVM bytecode dynamically to run it at the best performance. But you can mix SQL queries with this low-level API if you want to. So just as an example, well, actually, let me go through these details, and then I'll show you an example of this. Hive is a SQL tool that's very popular in the MapReduce, or rather the Hadoop world. And of course, any mature Hadoop organization is going to have a lot of data organized. They're all files, but they're still organized as Hive tables, so they can write SQL queries. And you really need to be able to interoperate with that. So Spark gives you a way of directly running Hive queries if you want. And this is really a nice way of doing extract, transform, and load, or ETL. I can use all of this, facilities that I have for Turing-complete computation with Spark, but I can generate data in Hive that my data analyst can then use with regular Hive tools or Impala, things like that, if you know what those are. They've built in some nice features, like they'll automatically infer the schema of JSON formatted records if your data's in JSON format, and also write JSON in a nice way. There's a very nice file format that's popular in Hadoop called Parquet, which does column storage and compressed columns and all kinds of stuff. So that's sort of like the gold standard now when you're writing data to the Hadoop file system, for example. But that's really easy to do with Spark. And because of the performance of Spark and that optimization I mentioned earlier about not writing to disk all the time, you get tremendous performance improvements over Hive. In fact, there's now a project to take the MapReduce core of Hive and replace it with Spark. And those of you that may know, that was actually done once before. There was a tool called Shark that did this. This is a more engineered approach. Anyway. So let's actually look at this, and I'm going to mix in some machine learning code, which is another one of these layered-on APIs on top to sort of mock up an example. This is actually based on a real sample that comes with Spark, but I've dumbed it down just a little bit for the purposes of the talk. Let's see, how am I doing here, by the way? Okay. So imagine I have like a user table, and this is exactly how I might declare this table in Hive with Java-ish types. I've got users. The key things I want are like the user ID, their email, and where they're located, their latitude and longitude. Those are the key features. And then I've got some events that are going to be coming in from like a mobile device, with some identifier of the user and something that they did. And now I'm going to mix SQL and Scala. So notice what I've got up here. I've got this method SQL. I'm leaving off a few details like imports and things like that just for concision. But notice this SQL query. I'm just embedding the SQL query. And what I'm actually doing here is getting some training data that I've got about what's happened in the past that I want to use to train a model. And then there's some business in the machine learning library where I want to convert this to labeled points. A labeled point would be something like if I have email and the vector of features is like the words that might appear in my corpus. The label would be whether this is spam or not, that sort of thing. In this case, the label might be they're interested in a particular kind of offer from my services or whatever. Now, one of the ways that you can predict whether someone would be a good fit for a particular offer is a tool called logistic regression, and SGD is stochastic gradient descent. It's just a way of like iteratively training the model to match the data. And somebody's working on the model in the background, as you can hear. So then another SQL query. So now I'm going to query my users and find out who isn't already subscribed to notifications. That's basically it. And I'm just going to pull off the fields I care about. And then I've been training my model, so now I'm going to predict, based on the model, whether the user is going to be a good candidate for features, given their location and their age and that kind of stuff. I'm sort of glossing over a lot of details here, but just to give you the gist of it, I'm going to take that result, which was an RDD, and I'm going to turn it into a table. And so I can write new queries against that. And the last query I'm going to write is a join of the scores and the users, and then find the top 100 people that maybe I want to send email to and say, hey, you should sign up for this offer. You're missing a great opportunity. All right. So now, would you do this in production? Well, obviously, I'm doing stringly typed coding here with these SQL queries. I won't know until production or test time that I've got bugs in those SQL queries. So if I was actually going to build a job and deploy it, I would probably use the new data frame API to basically write the same thing in a type-safe way. However, if I'm in the shell and I'm interacting with my code, sure, I'd write SQL queries like this because they're very concise. I know SQL. If I make a mistake, I'll know right away that I made a mistake. So you more typically see people write SQL queries when they're working interactively, but you could do this in production if you wanted to. And that's what this all looks like. But the cool thing is you basically pick the best tool for the job. And again, this is based on an example that comes with Spark when you download it. I mentioned earlier that MapReduce had this problem that it doesn't handle batch mode processing. Or that's all it does. It doesn't handle like event streams. Well, it turns out Spark doesn't either. At least it didn't initially. It also emerged as a batch mode tool. But because it's a very lightweight system, they actually found that, if we actually do mini batches, like let's say we capture events, like in 10-second batches or some arbitrary number of seconds, and then treat those as a little mini batch job, that actually works. And that's going to solve most of the needs people have for streaming. It won't solve the problem where I need to react to individual events. It's not a tool for that. But if all I want to do is shrink that time between data arriving and information being extracted, this is probably all I need. And the other advantage is because it's actually wrapping the batch mode code, I can actually write one chunk of logic that I can run in batch or run in streaming. And if any of you have ever done the Lambda architecture, which is this idea of combining stream processing with batch processing, probably the biggest flaw of it was that you typically had separate tool chains for each of those, so you kind of wrote logic twice, was a pretty common problem. This problem goes away here because I can basically reuse that core logic in both contexts. So it looks something like this schematically. This is a variation of that RDD chart I showed you earlier, where now each of these time slices or batches will be put into an RDD. And as soon as one finishes, some arbitrary number of events show up within, let's say, 10 seconds. I'm going to capture those into an RDD, then start processing them while the next batch is being captured. And they also give you windows. So if I want to do like moving averages, let's say, over the last hour of these 10-second windows, I can do stuff like that. And they call these a discretized stream, or D stream. But the code is very similar. So just to very quickly show you what it looks like, I start with a Spark context. I think there's yeah, there it is. I wrap it with a streaming context where the second argument is a fixed size for batches. And I'd kind of like the flexibility, actually, to make that variable. But nevertheless, that's the choice they made. There's several ways you can ingest data. You can pull it out of Kafka, Cassandra, Twitter Firehose if you have a Twitter account. In this case, I'll just listen on a socket and expect text to come in, regular ASCII or something like that, or UTF-8 or whatever. And just for simplicity, I'm going to do that word count thing where I'm going to forget where the words originated. In this case, they're all coming from the same place. I'm just going to count the number of words I find. So I do something very similar to what we saw earlier. I flat map to split each of these lines of text into words. I add a seed count of 1. So I'm creating a tuple with the words and adding a seed count. And then I'm going to do that reduce by key trick to sum up the counts. So kind of the code we saw already, basically. And then there's a slight variation for the output. This will write a new directory of output files every 10 seconds, which may be too much, but that's sort of the default way of outputting it. Once again, I'm setting up a pipeline, and then I start it, and then I wait forever for it to finish or die, which is probably what's going to happen. But the point is that logic in the middle was very much the same logic we already had, obviously simplified for the example. But the wrapper around it was the streaming stuff so that I could reuse the core logic if it was in a library. Okay, and I'm just going to briefly mention the last two and then wrap up. We actually saw a little bit of the machine learning library called MLlib that's available. It's a rapidly growing thing. Actually, one of the nice things they're doing is they're adding algorithms that are specifically oriented towards streaming. Like, for example, if you want to find clusters in data as it's arriving, you can do it in a streaming context. And there's also now, because there's efficient computation and the ability to iterate and stuff like that, there's some graph primitives built in, so you can traverse graphs. And if you went to Paco's talk yesterday, he talked about this in depth, the GraphX library. So just to wrap up, then, Spark is this flexible distributed processing system written in Scala, leveraging the power of Scala, exposing Scala-inspired APIs with some optimizations and extensions, supporting other languages, supporting higher-level abstractions like SQL and graph processing and so forth. And before I take questions, my old friend Bill Venners has something he wants to tell you.
Have a book signing at lunchtime at the Workday booth. Andrew Phillips, one of the co-authors of Scala Puzzlers, is going to be there, so you can meet him and talk puzzles. And it's it's like half price rounded up to the nearest multiple of 20 euros, which is 20 euros, so it's a good price. And we're going to give away 6 free copies, 3 to lucky people in this room. I'm going to toss these out. These are little puzzles. If you catch it and make it into a cube with the puzzle pieces, then bring it to the book signing at lunch at the Workday booth, and we'll give you a free copy.
All right. All right, heads up. You didn't need that face, did you, sir?
Over here somewhere. Woo. All right, that's it.
All right, thank you. All right, thanks, Bill. Okay, a last picture of the London Eye in Parliament. Wrong country, I know, but hopefully you'll forgive me for that. Anyway, thank you very much, and any questions? Yeah, we have about 5 minutes. Stunned silence. Yes, sir. Go ahead and yell it out. So the question was, what about spatial data? Are there any sort of like optimizations or support for data that's very spatially oriented? I kind of gave you a sort of a crude example of that with this machine learning example. I don't think there's anything built into Spark specifically about representing spatial data, but the nice facility about it is that you can plug in data structures and algorithms pretty easily that will support it. Some friends of mine that work on the Spire machine, really a computation library for Scala, they've been working on some spatial data structures, I've noticed. D6 is the Twitter handle for the guy that's doing this. You should also probably check out Paco Nathan's SlideShare feed, because one of the things I love about his talks is he often has really, really good, realistic examples and lots of research, links to research papers that discuss stuff like this. So I bet he would have an example of people actually doing this already, but I don't actually myself. Anybody else? Is there also a what? I didn't quite catch it, sorry. Yeah. For .NET? That's a good question. So I know that you can now run Hadoop on .NET, or at least Azure. Hortonworks, one of the Hadoop vendors, did this. They're now supporting Spark, so in principle, you should at least be able to run Spark on .NET. I don't know yet. I haven't seen that anyone has done .NET language bindings like F# or C#. I know there's one for Clojure, for example, that isn't part of the distribution. The fact is, because for any JVM language, it would be relatively easy to do just by talking to the Java API if necessary. With .NET, you'd have to be able to connect to the running JVM system, and because you're going from one language environment to another, there'd be a little bit of a challenge there. But you could reproduce what they're doing with Python, basically. Actually, I think they're using Jython now, so that may not be a good example. But anyway, I don't know of anybody doing it yet. Anybody else? Oh, yeah. Yes, the question is, are there preferred graphical front ends like environments? There's actually too many. There's a bunch of people who've written variations on IPython notebooks. There's actually an iSpark. You can Google this. It's a Spark backend for IPython or Jupyter. There's Spark Notebook. We actually had a talk yesterday afternoon by Andy Petrella, who's the main guy working on Spark Notebook. What he did is he forked a Scala notebook project and basically plugged in, or just replaced the Scala REPL with a Spark backend. And we're actually thinking of maybe supporting that for TypeSafe for our customers. You can certainly use Eclipse and IntelliJ for the developer side of things, but there are several IPython-like notebooks out there. The other one I'll mention is Zeppelin, which is an Apache project that's pretty nice. Anybody else? Yes. Right, so that's a really interesting question. Let's see what we're doing for time. What's the shortest time you could put in for streaming? Sort of the rule of thumb is no less than half a second. And from what I understand from talking to some of the guys who are Spark committers, you actually run into limits about internal communications. The way they've implemented things, you actually can't reduce it any farther than that before you start running into just too much overhead doing other JVM things. I think it's involving the way they manage memory, and there's some network issues they've run into trying to run smaller batches. So if you really need something that's more like, down to millisecond ranges, you would want to use Storm or Akka Streams or something like that. Right, so like integrating a bunch of different streams at the same time? Yeah, the way that you do that actually is you hook up a listener for each stream, but then there's a union method that you can call to actually union the streams. So you don't do anything other than that to actually like multiplex input. Does that make sense? Okay, I think we're about out of time. Thank you very much.